Couple things. First of all, I don't have any Scantron scores yet, and I'm still working on the self-paced polling SPP data that you'd use with your clicker. So we don't have any data on exams yet. And with the Scantrons, it's kind of hard to predict. I know a few of you asked me, Dr. B, when will these be graded and stuff? And I can't ever really tell you, well, it'll be graded by 3 o'clock or even a day. It's unpredictable. You know, sometimes I have it back the same, like after this class, we dismiss at 12, right? And so if I went down to the test center, which is actually in this building, at 12:01 and dropped it off, I might have it back by 1:30, or it might take, another couple days. So you just never know. And so I might, we might have them this afternoon. And when we do, I'll post those in web courses. So what you'll see in your grades page are 3 new lines. The first line for the Scantron part of your grade, the second line for the clicking part of the grade, so that'll be, something out of 5, and the Scantron will be something out of 45. And then the third line will be below that, which is just the total of the first 2. So that'll be your total exam 1 grade. And you'll see that. Now, a couple things. In a class of this size, almost 300 of you in this section alone, there's a lot of Scantrons, and I was trying to keep an eye on everybody's Scantron as they turned them in, so that I could make sure that everybody bubbled in their PID and test form A, B, C, or D. So if you messed up your PID, I don't know your PID, so you have to do that properly. If you mess it up with the wrong number, or one of the bubbles is not dark enough, or the same thing with the test form, you don't bubble that in, or it's not dark enough, then you'll have a blooper. And but if you didn't do any of those bloopers on your Scantron, you'll have a grade. And just so you know, when I do post the Scantron scores, if you were here but you get a -1, that means that your Scantron is blooped up, and we'll try to get it sorted out in the next week or so. I mean, it's not like you're not going to ever get a grade, but we got to go through the Scantron pile and find yours. It's unalphabetized. And then we got to look at your exam, and that pile's all unalphabetized. So it can be kind of a pain in the you-know-what, but it will get done. So, but hopefully everybody said, oh, you know what? In the summer, I had a big lecture class about this size, different lecture hall, but we came to an agreement. A student, because I told the students that on one of their midterms, nobody had a blooper on PID or test form. So there were no exams to dig out of the pile or anything like that. Everything was perfect. Everybody had a grade. So somebody up in the cheap seats at the back of the lecture hall said, "So Dr. B, that means we get bonus points?" And I said, "Yeah, okay." And so we did that. We did it for the third midterm, and we did it for the final. And they did. They got bonus points. So I think for next exam, if everybody gets their name, PID, and test form in there, no bloopers, I'll give everybody a bonus point. Okay? So a little help for your grade. Anyways, let's keep going. I have some questions that I want to go over with you concerning hurricanes and stuff. We're going to do a short answer question. We're on frequency DD. And this first one is kind of a public opinion survey. So just whichever one you answer, A or B, is going to be marked correct. Go ahead and start with this. And make sure you hit the send key type in your answer and hit the send key. And either answer is fine, so I just want to know which ones you think are. And this is actually going to be related to our discussion today, so. No C. No. If you typed in a C, you know. All right, good. You give me A or give me B. Okay, 20 seconds to vote. No D. Only A or B, one or the other. Ten seconds to vote. 9, 8, 7. Look, typing in hello and hi is nice, but I know who you are, and it doesn't impress me. I'm asking you a physics question. I'm not asking you stuff for fun and games here. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Good. 176 people. Majority voted for B. And before we go and talk about that, we're going to do another question here. So hit the refresh key on your calculator or your clicker, and let's do another short answer one. And my short answer question for you is, why did you answer that way? Give me type in your answer, A, and then the comma, or B, and then the comma, and then your one word or a short phrase about why you answered A or why you answered B. All right, let me start it. Okay, so you can start. And this, again, is a legitimate question, so just type it in, gobbledygook. So A, comma, and then your word or phrase. Or B, comma, and then your word or phrase. Or you could put a space. B, space, and then your word or phrase. It's interesting. And we talked about these quite a bit in the 9 o'clock class. And I could hear a lot of clicking, so that's good. And I'll go through some of the answers and grade a few of these. This one I'm going to grade. So if you're writing in something that's a bunch of numbers or something, I'm not going to grade it correct. And don't forget to hit the send key when you're done typing in your answer. What is it that makes A or B most dangerous, in your opinion? And you can change your mind if you feel like it. What's that? I can't hear what you're saying. Yeah, I think you have 16 characters maximum. So you can't write a sonnet or anything, but you can put in, A, comma, and then a word or two. B, comma, and then a word or two. You can't even write a haiku. But one or two words, yes, definitely. unless one of the words is anti-disestablishmentarianism. Or supercalifragilisticexpialidocious. Okay, 40 seconds. 40 seconds. Thirty seconds. Type the send key. If you don't hit send, it doesn't know when you've stopped. So you got to tell it, yeah, this is my answer, by hitting the send key. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2. Did she send the, Sadara, did you hit the send key? Sadara, did you get it? Okay. 1, 0. Okay. All right, let's take a look at the answers here. We'll see if there's anything interesting. Let me maximize this. Okay, so here's some stuff up at the top. Air whirls. Yeah, I guess you could maybe see that. But, you know, water does the same thing. BC hurricane. A, bigger. I'm trying to mark this correct here. What's bigger? Good question. But I mean, it's whoever answered this, and you don't have to raise your hand if it was you. You're thinking of but there's some quantity that could be bigger or smaller, and that for air that the quantity is bigger. Destructive, that's kind of a circular reasoning. You're basically just restating your answer from the other one. Divide. I wonder what that means. Faster. Okay, here's somebody else. Think 4 people. Faster speed. Everybody's thinking about numbers here. So you see how the numbers, you're thinking in terms of something that's... And here's another one. Force, MPH. That's a number. You're thinking numbers, the number of miles per hour. Greater speed. See how this is all in here? You guys don't think you're scientists, but most of you, more area. Not necessarily, but I'll grade that correct. More power. Anyways, what I'm going to do, there's a ton of answers in here. And look at this. Most answers, it's just one person. So, which is kind of cool. Tornadoes. Wind is powerful. Wind is staunch. I guess that means somebody forgot the R in there. Stronger. All right, that's good. Wind speed and ma. Something about the MOM, I guess. Anyways, I'll look through these later, grade them all. But here's the thing about it. As I mentioned, most of those answers, you're thinking about something, some kind of a number, something's bigger, something smaller, there's more of it, miles per hour, some kind of scale of measurement. And that is actually the crucial factor. In my opinion, water is the most damaging. Even though in this example, less water and a slower speed, but the amount of mass per second, even at a slower speed, is going to be the critical factor. Plus the fact that water is not very compressible. and air is compressible. Now, air does a lot of damage too, so you can't say that one's a walk in the park and the other one's a date with danger. But I would choose, and what Sir Isaac Newton would have said is, he would have chosen water because water has a larger quantity of motion. So go ahead and write down that phrase, quantity of motion. When Sir Isaac used that phrase in the very beginning of his famous book, the principles of the mathematical principles of natural philosophy, he was, remember this, did we show you this postage stamp last time? Last Thursday? This famous equation of his, delta mv. He was thinking about that. There's the impulse equation. The very first part of chapter 1, or chapter 4. And he wrote it in that way. That was his quantity of motion, mv. So not just the speedometer rating, and not just the mass, but the product of the mass. That's what he called the quantity of motion. Now, you can see it in this clicker question. Now, we're not going to do this as a clicker question, but I had it ready last time for clicking, but we'll just look at it. F equals m delta v over delta t. That's F equals ma, right? Just using the definition for acceleration instead of the letter a. So if you cross multiply and get delta t over to the left side, what's left on the right side? M delta v. And so this equation, as I mentioned last time, for you to look at, the impulse equation, that is actually a restatement of the second law, but in the terms that Sir Isaac Newton thought about the second law, which was in terms of forces and interaction time and in terms of quantity of motion. And as I mentioned, this is actually for the first couple paragraphs of 4.1. Now we're going to talk a little bit more about 4.1, and then we're going to dip backwards into chapter 3 and get that finished. But let me just add something here about what I said about Sir Isaac. He said that the quantity of motion is what forces act on. But now what we use in modern parlance is the word momentum. The equation for momentum is this one. P equals mv. You can write it as a vector statement with those little arrows over the top of the symbol P. P is the customary symbol for momentum. I do not know why we use that. I suppose some historian of science knows. I don't know. But anyways, P, symbol for momentum. This one has an arrow over the top of it to reflect the fact that it has a direction. It's got a length and a direction, so we can represent it with an arrow. It's a vector. And the vectorness, the directionality comes from the velocity vector. And we know that that is expressible as an arrow that has a certain direction in space. The mass is the other factor in the definition of momentum, and mass is just a pure number, a number of kilograms. It's a count. It doesn't have a direction. In other words, there's no leftward mass. There's no northward mass. There's just mass, So that's what Sir Isaac Newton, that's his phrase, quantity of motion, in our modern parlance, momentum. Now, a couple things else that I want to mention about that, and that is Albert Einstein's theory of relativity, he generalized the idea of momentum to being a four-dimensional quantity. His whole thing was, that the universe is not just three spatial dimensions, X, Y, and Z. He said you've got to think of time as the fourth dimension, and that the universe itself is what we call four-dimensional space-time. And he said, because of that, our dynamical quantities should also be four-dimensional. And he developed his theory in terms of this four-dimensional momentum, in which the very first part of it is actually the energy, like the kinetic energy of an object. And then 3 slots after that for the m times vx, m times vy, m times vz, the x, y, and z component of the momentum arrow. And then the fourth dimensional component is actually the energy. Now, we're not going to be using too much of his four-dimensional space-time, but yeah, it's in there. And the interesting thing is that the symmetries that we find in nature are encoded in terms of momenta. In other words, when we find that there's some law of gravitation or some law of quantum mechanics that has a symmetry in it, the way that it shows up is treating momentum vectors and momentum for vectors like this symmetrically. And we'll talk more about symmetry as we get deeper into chapter 4. By the way, you can start reading ahead into chapter 4, and I believe that the chapter 3 mini review, has anybody tried it yet? Has anybody seen it yet? Nobody? I believe the chapter 3 mini review is actually supposed to start as of, I don't know, today or yesterday, and goes until the next exam. But that's, we'll have some homework this weekend in web courses. And here's a picture. Now, you may have, remember we talked about skateboarders pushing off of each other. Let me ask, who's got a skate? I know some of you guys have got skateboards. Who's got a? Rachel, come on down the front. And Sawyer, come on down. I know you got yours. And what we're going to do is okay, I want you to stand right down here in the front and in the middle, and I want you to stand next to each other, face to face, and I want you to go patty cake like this, okay? Okay, so get closer, yeah. Okay, okay, and I want you to, when I say 3, I want you to push off of each other, okay? Now, don't fall on your keister. Okay, try not to, because we did it for the 9 o'clock class the other day, and so one of the students almost fell on her. So anyways, all right, you ready? So you ready? 1, 2, 3. Yay! Now what we saw is 2 skateboarders of different. Let's try that again. Let's switch directions. Let's see if there's any difference when one goes left and one goes right. Sawyer was pushing to the left, but he went to the right. And Rachel was pushing to the right. Hold on. Wait till I say. So Rachel was pushing to the right, but she went blazing off to the left. You know what that is? Newton's third law. Okay? So here we go. So we're talking Newton's laws here. This is an interaction. All right, let's try it one more time. Get real close. Get yourselves a little closer. Okay. Okay. 1, 2, 3. All right. Now they went different distances. Okay. And it's because they're 2 different masses and stuff like that. Now, okay, thanks you guys. And let's give them a hand. So this whole idea of skateboarders exchanging, what is it that's equal but opposite? The interaction force is equal. You already know that. from Newton's third law. The contact time is equal. You know that from common sense. And because Rachel can't be in contact with Sawyer any longer than he could be in contact with her. So F, the interaction time, in the impulse formula is the same size. Delta T is the same. So that means that the delta P that they're exchanging momenta. That's the interaction. And that is equal but opposite direction in the skateboard interaction. So you're going to have some homework here. You know, you could have a hokey looking diagram, a couple skateboarders, and here's like 1/10 of a second after they release. Okay, and you're going to have some masses, Raymond for red, Gregory for G, green. And there's going to be an interaction time and a mass. And a little bit further down, there's going to be a force of the skateboarders of interaction. And you're going to do some little calculations. And that's going to be in your homework for the weekend. And I'll have it ready for you by lunchtime tomorrow, if not sooner. But it's going to be, you know, about skateboarding and stuff. So let's take a look at impulse. Let's work out some examples of impulse. And F delta T, that's the impulse. And that corresponds to the change in the momentum delta P. And so, you know, we're going to be talking about this. There's the definition of impulse, F delta T. So your contact time or your interaction time, for skateboarders anyways. And then the third law, force equal but opposite. So the F that when you're calculating an impulse, you might want to keep the direction in mind. If you have a fancy calculation, and we're going to do a calculation together here in a second, you will want to keep the directions in mind. Okay? Sometimes, oops, wrong direction. Sometimes you see impulse written this way. I do not write it that way, but you see it, you know, various places on the internets, F times T. But you know, the F delta T equals delta P, the change in the momentum. And this is the other equal thing that's exchanged. So they have equal force. They don't really exchange forces. They each experience a force. And they don't really share a time. They both have a duration, a common duration. But the thing that they do exchange is momentum. And so an interaction is an exchange of momentum, delta P's. And just to reinforce, this is just another version of F equals ma. But it's a version of F equals ma, Daniel, that allows us to eventually see symmetries as they occur in nature in a way where you can actually see something as symmetric. You know, the forces you can't always see as being symmetric, but the momenta, yeah, a lot of times. All right. Now, the other nice thing about this, delta T is up there in the equation by itself. We factored it out of the acceleration definition. You know, so I mean, we could put it back in there if we wanted to, if we needed. But if you're thinking about anything, you know, like a stopping time, you know, like we talked about doing a plyometric workout and how you bend your knees a little bit to make your stopping time a little bit longer and easier on your joints. Delta T stopping time, yeah, the impulse formula gives you a fairly basic and easy way of calculating stopping time. Now, this weekend, you're going to have a homework. It'll be homework 6, due on Tuesday. And it'll have a question. It might even have this question about a coin of mass 0.05 kilograms sliding across the tabletop from left to right. Now, notice in this problem, the way I've got it set up, I'm distinguishing directions. So then we'll take careful notes here. And, you know, we're going to have pluses and minus signs. Pluses to denote rightward and minus signs to denote leftward. All right? So we have a coin, a mass 0.05 kilogram, sliding across the tabletop from left to right. At initial point x1, its speed is 1.7 meters per second rightward. And notice that I use the word rightward there. That's perfectly fine in a sentence. Now, in an equation, we'll use a plus sign or just a regular 1.7. It then experiences a frictional force, F equals 0.020 newtons leftward. Now, that one is perfectly fine in a sentence. But when we put that one in an equation, like the impulse equation, we're going to want to use a minus sign to denote leftward. All right? So it slows down to a stop at position x2. What is the stopping time for this coin? So stopping time, that's delta t. So we're going to use the impulse formula, F delta t equals delta p, and just kind of solve for delta t, the stopping time. Because we have the, if you think about it, in here, we have everything we need to figure out the initial and the final momentum. So we can get delta p. That's the right-hand side of the impulse formula. And we have the frictional force. That's 0.020 newtons to the left. So that'll be a minus 0.020 newtons when we put it in the equation. But yeah, we got that. And that'll encode the entire stopping interaction of the coin with the tabletop, the frictional interaction. All right, so there's my setup. And when you guys are doing your homework, when you're doing your exams, always read really carefully. Read for information. All right? And don't use every bit of information, don't use every number if you don't think it's needed. You got to know. Because sometimes I'll write a question with more than one number, one of them which you don't really need. Right? So don't let me catch you napping on that. Always read carefully. So here's our example. Here we go. P1, initial momentum. All right, there it is. MV, the mass is 0.05 kilograms, and the speed is 1.7 meters per second rightward. And hey, you guys, the metric unit of momentum is just kilogram meters per second. There's no fancy name for it, like a Bernoulli or anything. Newton, it's the unit of force. But we don't have one for kilogram or for momentum. All right, now, that's P1. That's the initial. And notice that I've put a plus sign in there now. In the second line of my equation block, I just have P1 as a vector equals and a plus sign to denote rightward. Right? I had the word rightward up above there after the comma, but now here in the second line, I've got it as a plus sign. And P2, that's centri. Is this 0? Because it stopped. So stopping time problem, you're always going to have the centri momentum when it stops. 0. Bing. Easy to write down. But one of them you're going to have to calculate. It's all right. Anyways, so with these two babies, now we can put together delta P. Because remember, the impulse formula, F delta T equals delta P. So we want to get we want to get the F, we want to get the delta P, the change in the momentum, and then we want to get the solve for delta T, the stopping time. So here we go. All right. So here's delta P. Final minus initial, later minus earlier, P2 minus P1. So 0 minus 0.085 kilogram meters per second. All right, so delta P is, now here we're using the minus sign here in the second line of this second equation block. Down here, we're using the minus sign to denote leftward, because that's the change in the momentum. And what one way to interpret that is that you've lost rightward momentum. Go ahead and write that down. A minus sign here means you've lost rightward. Now, if he were moving to the left and that was the delta P, then that means he would be getting faster to the left. But this one, he's moving to the right initially, and he slows down, and he comes to a stop. So his delta P is negatory to the left. All right? Now, that negative sign, we're going to leave it in here. Now, you don't always have to do this, because we're going to find out here in a second that the negative signs cancel out. But I'm carrying all the minus signs very carefully in this example, and you can do this too. Now, here's the impulse formula. F delta T equals delta P. And now I'm putting in everything that I've got. I've got my leftward 0.020 newtons. And then delta T, which is my objective. That's my target. I want to get that one by itself. And then on the right side there, in this third equation block, I've got negative 0.085. Now, if you want, you could cancel the negative signs now. Because look at that, left and right. Bing. Yeah, you could cancel those. That's kosher. I'm going to keep them. But, you know, just remember here in what we're doing that you can cancel them now. And really, if you don't really care about the direction, left and right and stuff, sometimes you don't even need it. All right? And we'll do an example of that in a minute. All right, so here's my, let's just make a little more room here. So there's my impulse equation, and I still have my minus signs in there. That's all right. And here's the plug-ins. The known value of the frictional force, and then the calculated value of delta P. And so plug those in. And now we want to clear the left side. And our method for doing that is to divide both left and right by negative 0.02 newtons. And so if you do that, then you've cleared the left side. And now you have delta T by itself. And notice that here you can cancel the negatives as well, you know, because negative over negative is positive. You know, so this is a place, you know, so you don't always have to cancel it at the same time as your neighbor. You know, you get a little bit of, you know, leeway as to how you decide to do that. All right, so now you just compute. Anybody have an answer? Anybody else with 4.25? Verify back there? Okay. Anybody in the middle? 4.2. Got it? Blue t-shirt? Okay. 4.2. Sodora, 4.25? Okay. You got 4.25? Okay. What is your name? Rosie. Okay. Thank you, Rosie. All right. So delta T is 4.25. And so if I ask you to round off to the nearest tenth, you'd go 4.3. You know, and then type that in and then hit the send key or, you know, whatnot. And don't forget, when you're doing homework in web courses, they always add those extra zeros in there. Don't pay any attention to that. Doesn't affect the answer. Now, we're going to do some impulse equations, but let me pause for just a minute if you have a question about anything that we've done. We've gone step by step, but I don't want to, you know, we'll double check something here. Go ahead.
I'm just wondering, like, for all of this, what would you use it for? Like,
well, this is an example of figuring out a stopping time. So remember, what we want to do is try to predict a future state, if we can, of some physical system. So one of the ways to do that is to figure out how soon it's going to stop, stopping time. Another thing that we'll do next week is stopping distance. That uses energy and work, and that's really easy. But that's another, you know, where's it going to stop? So, and these are really basic examples, but if you think, you know, down in Houston at Mission Control, you know, they got half the PhDs on the planet figuring out, you know, the impulse equations for these big complex spacecraft and stuff. You know, because they want to land, I mean, they want to land at a certain place on Mars, and not crash land on the, some other part of Mars, or totally miss Mars and go flying off to Pluto or something, which has happened. If you read the introduction to the textbook, you know that there's a famous crash that, somebody blew it with the calculations, and the mission had a catastrophic failure, crashed on the surface of Mars. Anyways, so that's kind of what we're trying to do here. And these are kind of simple things, but, Hidden Figures, they take the simple things and then do a zillion of them. And they put John Glenn where they want him, within sight of the aircraft carrier when he lands. So it may seem simple to us guys, but, All right, so let's try some simple calculations. Hit your refresh key because we're going to do multiple choice now. And we're going to do just a simple impulse calculation. So make sure you have your notes where it says the definition of impulse. And then we're going to do a fairly simple stopping time calculation like the one that we just did. And we'll review the stopping time calculation. But the first one we want to do is a blob of green jello floating in space. All right, so this is just how much impulse. Now this one's not asking a direction or anything, and the next one isn't really asking a direction. So you want to, just use your impulse definition, and you'll be good. And let me see what you guys are answering here. Would you guys like to dismiss a little early today? Yes. I mean, is there anybody that doesn't want to dismiss early? Get out of here. These guys back there. Okay, that's it. No dismissing early. All right. Now, I think we'll be able to dismiss a little early. But I haven't figured out which section is smarter, the 9 o'clock or you guys. Hopefully, I have a feeling it's you guys, but I just, I have to verify. All right, so make your calculation, and this one has a correct answer as well, so I'll be grading this one. Use the definition of impulse. This is multiple choice, so hit the refresh key, type it in, and just hit A, B, C, D, or E. You got, is it clicking now? 45 seconds. Read carefully and use your definition. 25 seconds. What? Is it working? Is it working now? Yeah, okay. Yeah, this one you use the buttons for A, B, C, D, and E. Okay, 10 seconds starting now. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Raise your hand if this is your last class of the week. So if we dismiss early, it's good. You're out of here. That's good. All right, I think we can dismiss early today. But we got a bunch of more work to do, but hopefully we'll. All right, so 0. 185, yep. The majority or a plurality got this one right. Here's the answer. 24. Yeah, F delta T. The force, the tractor beam, 12 newtons, 2 seconds, that's delta T. Ding, 12 times 2, 24. And shh. Hey, you guys. A newton times a second, you might want to write this down. 1 newton times 1 second is a kilogram meter per second. Because a newton is kilogram meter per second squared. So if you multiply by second in the numerator, you cancel out 1 from the bottom. And you're left with kilogram meter per second. So in the metric system, Newton second is a unit of momentum or impulse. You can think of it that way. All right, next question. And this one's a calculation all the way, so do this one carefully. Basketball of a mass 0.800 kilograms. Initial speed 22 meters per second. Stopping time, just like the one we did with the coin. But this is a little bit bigger. 11 newtons. Now you don't have to do directions, but if you do it the same way we did, with minus signs, they'll cancel out and you'll just have a positive number, some fraction of seconds and stuff. And the correct answer's up there. So this one's taking the full calculation. If we dismiss early, I could sneak over to Chick-fil-A and get lunch over there before the rush. Because that line over there is... Did you ever notice that line? It's like about 5 miles. This time of day, you got to wait about 9 hours to get nuggets. $45 seconds. Yeah. 30 seconds. You guys are doing good. See, that's interesting. You didn't get the previous one, the easy one, but now this one you're getting right. That's good. I like that. I'm happy about that. So maybe this is the genius section. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, good. 1.6. Let's double check it. Yeah, we got a bunch of you blooped it up. Here we go. F delta. Just, whenever you see stopping time, this should be your first instinct. Use the impulse formula. Now, sometimes you can just go back to F equals ma if you feel like it. There's no, no skin off your nose for that. But this one's maybe a little bit simpler. All right, so here's your initial calculation of the momentum. 0.800 times 22, 17.6 kilogram meters per second. So that's the right side. So now I've skipped, the part where it goes 0 minus and 17.6 kilogram meters per second. And I've skipped, I haven't put any minus signs in for directionality. But I mean, if I did, I'd have a minus sign over there with the 11 newtons, and then it'd cancel. So I pre-canceled to make things simpler, all right? And there's my stopping force, 11 newtons, all right? And so here's my quotient. Divide both sides by 11 newtons. And you know, a newton divided by kilogram meter per second, you know, that kilogram meter per second can be replaced by NS. You know, you should all write that down. Write down this last one. Delta T equals 17.6 NS, Newton seconds, divided by 11 N, 11 newtons. Just so you remember. Because, you know, it makes it handy to cancel. Okay, now you don't have to do that, but if you do, it's one of the ways that I do it. You know, canceling units and stuff, I see your question, I'll get to you in a second. If you're canceling units and stuff incorrectly, you know, you're looking for a seconds, you know, some kind of a duration in seconds, and you come up with meters per second, then, I blooped something up. It should tip you off to go back and double check your calculation. You know, like maybe all the way back to the formula stage. All right? But anyways, on this one, you know, 1.6 seconds is your answer. Question? Yeah, it was in the problem. You know, it's the stopping force. All right. Now, we're going to go back into chapter 4 next week, but right now I want to dip backwards into chapter 3. All right. And I want to talk about uniform circular motion. And what we're going to do is use some geometry concepts that you might have thought, I'll never use them. You know, you're in 10th grade geometry, and you say to your loving, patient geometry teacher, when will we ever use these proportional triangles, similar triangles? Well, you're going to use them today. And we're going to figure out something about what NASA does with satellites. That's the payoff. There's a circular test track for cars, testing cars, in a place called Nardo in Italy, the Nardo Ring. Here it is. Here's a picture. It's from Google Maps. It's in the boot heel of Italy. You know, so you go down, you go to Rome, you fly into Rome, you head south, go over the mountains, and then over to the boot heel. Yeah, here it is, Nardo Technical Center. You know, go past Naples and then go over the mountain. Here it is. You can see it here. It's a circle. The radius is about 2,000 meters. So it's 4 kilometers across. There it is. It's a view from space. Get a little closer. And you can see they got all kinds of buildings in there. And then but a lot of it's looks like cultivated fields, you know, agriculture and stuff. But that ring, here's the overhead view. That's what we want to talk about. So the Nardo Ring, it's a test track for automotive manufacturers. So the automakers in Europe, they ship their cars down by truck, and then they run them, you know, for, 1,000 hours. You know, they just switch drivers, and, they run it until the wheels come off. Because, it's a torture track. They're testing their machines. So let's talk about the Nardo Ring. The Nardo Ring is banked all the way around, very precise angles. And the outer lane is banked so that you can go at about 149 miles per hour with the steering wheel straight. You don't have to, add any extra English. Just keep the steering wheel straight, stay on the track, keep it at 149 miles per hour, and you're good. And you may be saying to yourself, Dr. B, this is nice, but why is Fiat testing its cars at 149? Why is Volkswagen testing its cars at 149 miles an hour? Why is Volvo testing its vehicles at 149 miles per hour? The reason for that is over there in Europe, they got these things called the Autobahn. And on the Autobahn, anybody here ever been over there and driven on the Autobahn? Nobody? You have? Did you go any speed you want? The Autobahns, man, they're designed for speed and, whatever you think is safe. And, so that's why they do it. That's why they're testing at this speed. And that's why they make all those good cars like Ferraris and stuff over there. We couldn't really, you can't really get away with a Ferrari here. Can you imagine driving around Orlando in like a Lamborghini or a Ferrari or, some kind of a nice car? I mean, you're at lights and stuff. Those things are born to fly, to be free, not to be stopped at a stoplight with a minivan in front of you. But out in Montana where I used to live, it's pretty nice. I think a few other western states used to be like this. Out in Montana, it's the same thing. The wide open spaces out there, the distance between two small towns, 30 miles, the next big town where there's a, Costco if you want to go shopping, is maybe 100 miles or more. This big, wide open. It takes over a day to drive from the southeast corner of Montana to the northwest corner, diagonally across the state. It's enormous. It's further driving from the northwest corner of Montana to the southeast corner than it is from the southeast corner to Texas. It's unbelievable. So out in Montana, these distances, Laura, you know what they do? No speed limit. At least that's the way it was for many years until the federales said, no, if you're going to take our Department of Transportation money, you got to have a speed limit. So they said, all right, we'll put it, But it used to be during the daytime, whatever prudent speed you wanted to do. So 149 or higher. Now, I never drove that fast. But, the speed limit sign, there was two speed limit signs. One said, one was in black with white lettering, and it said at night. It was daytime, any speed you want. Daytime, 50 or 70 or whatever, whatever they had posted. But during the daytime, just crank it, my friend. And then, I don't know when it was, 70s or 80s or something, they said, well, you got to have a speed limit. So they said, all right, we'll have a speed limit, maybe in the 90s. And, okay, we'll have a speed limit. So they said, yeah, okay, we got a speed limit. Ship that money back. The Department of Transportation, all that money and stuff, ship it all back. And so they, and the way we got around it was, and the feds couldn't do anything about this. They made the speeding ticket $5. Not like around here. I went 37 miles an hour in a 25 mile an hour zone here a couple of years ago, $162 for 12 miles an hour. In Montana, they wouldn't even sneeze at that. But anyway, so that's how we get around it. The speeding ticket is 5 miles an hour, it's $5. But at night, they'll give you a big speeding ticket too. Anyway, so if you drive faster or slower, you have to crank the wheel. But if it's tilted, it's banked, like over here at Daytona and these, these stock car races and stuff, they got those big banked. Some of them are really steep too, to accommodate high speeds. So if you change the speed away from that optimal 149 miles an hour, you got to crank the steering wheel a few degrees. Now they have another one. The innermost lane is for testing trucks. So those are at a more realistic speed. Because trucks aren't going to be blazing down the Autobahn unless you got some kind of a maniac, that's, trying to, cause trouble. But faster than 50. So that inner ring at Nardo is a little bit different bank. And you can look it up. And all that stuff, you may think to yourself, well, why do you have to bank it? Because to keep yourself on the track in uniform circular motion, it takes a little bit of force. You can't drive it on a Teflon track with Teflon wheels. You got to have some grip between the track and what direction is the grip. If you're moving at a uniform speed, you're not speeding up. So the acceleration is perpendicular to the velocity. It's not speeding you up, it's not slowing you down. Until you hit the brakes, but it's the brakes that are slowing you down. But if you're at 149, for 7 hours, and, the force that keeps you on the ring is toward the center of the ring. Let me repeat that. The force that keeps you on the ring and not going up and over the side, sailing out to the wild blue yonder, that force is toward the center of the ring. It's perpendicular to your velocity, and it's toward the inside, to the center. Now, what we're going to do now is derive a couple equations on simple, concerning a simple circular path, kind of like Nardo. And then actually we're going to adopt it and use it and kind of insert it into Newton's theory of universal gravitation. All right, so here we go. Uniform circular motion. Okay, uniform circular motion, very precise definition. It means you're moving on a circle at constant speed. And what we're going to do is make a diagram at two different instants of time. So make a circle at instant of time t1, and go ahead and put a dot at the 3 o'clock position, and then draw a line segment from the center of the circle out to that dot. Okay? So it's a horizontal line segment. Now that's my black line here, and label that R for radius. And then we're going to say that this object, now I'm not talking if it's an atom or a truck or a Lamborghini at Nardo, but whatever it is, it's going counterclockwise. So drawing the velocity vector straight up. The velocity vector is tangent to the circle. And in this case, if it's going counterclockwise, it's not just tangent, but it's also upward. I mean, it could be tangent and pointed downward. That would correspond to clockwise. But if it's counterclockwise, it's tangent and straight up. If the object is at the 3 o'clock position. All right, so at time t1, it's at 3 o'clock position, position vector in black, velocity vector in red, and let's do another instant of time. Let's go a little bit further into time t2, and now put your second dot at 2 o'clock. So that's 30 degrees above there. All right, now at this later instant of time, t2, you've got a different position vector, all right? But it's the same distance, so you can label that one R. This is tilted 30 degrees up. And the velocity vector is tilted 30 degrees from, at time t1 it was straight up. Now it's 30 degrees. So here's what it was at time t1, straight up. At time t2, it's now about over here. All right? Now we're going to use, both of these things have tilted by 30 degrees. If this is uniform circular motion, same speed, same distance from the center. All right? So here's my two. Now I'm going to make these a little bit smaller, and I'm going to make some triangles here. The two position vectors in black, I'm going to put those two together into a triangle. And then the two red velocity vectors, the two red arrows, a 30 degrees separation, I'm going to put them both tail to tail and form another triangle. Okay? So let's do the position triangle here. Here we go. All right? So there's my copy of the position vector at time t2. All right? Now let me compare it to, just so I don't trick you. Here it is. Okay, so that's a copy. And now I'm going to put it down here to the bottom. So I'm going to put my sketch down here to the bottom. You put it wherever you want, wherever you got room. Now I'm going to do the same thing with the red arrows. Okay, so I'm going to copy them. There's my copies. All right? And they're kind of going up and stuff, but they're 30 degrees apart. All right? So there's a copy. All right? And they're tail to tail too. And so here they are. So here's a big sketch. So I made my two circles up and to the left. And let me just go through that again. Copy. Copy. Park that up to the upper right. Okay? And those two triangles are the ones that we're going to study. And from those two triangles, we're going to get a nice formula. And I want you to be very careful about these two triangles. Okay, so here's a bigger version of them. Okay, and here's a mini version of the full circles. Okay, now I want you to put a dotted. We don't really have triangles yet. We just have two line segments attached, 30 degrees apart. All right, let's make a triangle down here. Put a dashed line, and that's the position triangle now. And hey, you guys, that is an isosceles triangle. It's an isosceles triangle. Isosceles, I-S-O-S-C-E-L-E-S. Isosceles means two sides the same length. That's what we got here. R and R. Now we don't really know what this. There's no special name for this, but we can say that this dashed line is approximate distance. I mean, the true distance would be along a curve. So this is a straight line. It's a triangle. But it's pretty close to what the curve would be. So the curve, if you're on the track, and 30 degrees of going along the curved track is 90 meters, then this straight line segment might be like 87.2 meters. So it's pretty close. And if we chose two different instances of time, not with 30, but with like 15 degrees, it'd be even closer to the true distance. So we'll just call this approximate distance. Now let's go up here and draw on a base for this isosceles, and this is V and B. That's the velocity triangle. Isosceles, and it's kind of tilted, it's not the same tilt, but it's 30 degrees. The sharp angle of both of these babies is 30. And that means, okay, the sum of the angles is 180. So 180 minus 30 is 150. So the two bigger angles, what we would call the base angles, add up to 150. And they're both the same size. So these two triangles are 30, 75, 75. Go ahead and make a note of that. 30, 75, 75. And your homework, you're going to actually have to calculate base angles for different sets of triangles. Then they're going to get sharper and sharper. This is the first triangle. And we're going to do, like 2 degrees for the separation angle down here, the sharp angle in the homework. What do you call this red dashed line segment? What would you call that? I mean, the black dashed line segment, that's approximate distance. What would you call the red one? That red base, isosceles base. Give me a wild and crazy guess. Yeah, change in velocity, delta V. Ding. Yeah, that's the... From one to the other, yeah, delta V. All right, so that's good. And hey, you guys, these two triangles, yeah, they're similar. Similar triangles, proportional. So the angles are equal, the sides are proportional. That means we can put them into a proportion and be righteous when we do so. We're not going against Euclid or any of the other geometry experts. Also, this distance here, let's go ahead and write this down. Let's write that down as approximately V delta T. All right? So I'm going to change that. All right, so there's V delta T. Now, up at the top left here, you can see a proportion. And if you think about it, the top of both the numerator of each side of the proportion, the numerator is from the position triangle. And the denominator left and the denominator right, they're from the velocity triangle. All right? And that proportion is going to lock in our Nardo Ring uniform circular motion formulas. All right? Now, just to emphasize where these triangles come from, the proportion or the ratio on the right is the isosceles sides. Isosceles sides for the position triangle, isosceles side for the the velocity triangle. Right? Now, over here on the right side of the proportion, this baby, that's the base of each isosceles. So the numerator is the base of the position triangle, V delta t, and the numerator is the base of the velocities triangle. Now let me ask you a question. I want you to use your eyes. See if you can see anything. You see anything in that formula up there? You got all kinds of things pointing at it. You see, is there something squeezed in there maybe? You could see it, but it's like looking. You might, turn your head sideways or something. You see anything? What do you see? Students in the first class saw something. This is really the genius section. Somebody's going to see something. What do you see? Raise your hand if you see something. Laura. The V's, they don't cancel out because once on top on the right side, it's on the bottom on the left side. So you can't cancel those babies out. But good eyes, and because they're going to show up together as V squared in our final equation. Somebody up here. Cross multiply. Yeah, you can cross multiply. What else do you see? The V's, or there's something about the V's. You can't cancel them, but you can cross multiply them. What do you see? See anything? Anybody see an acceleration? You see acceleration in there anywhere? What do you see? It's a flip-flop. It's delta t over delta v. We got an acceleration in there. Let's get it out. Okay, Laura, let's cross multiply now and do a flip-flop. Bing! There it is. V squared over r on the right side and good old delta v over delta t on the left. Now, this is still approximate because we are at 30 degrees. But as you make this smaller and smaller, you just replace it. This, my students, is called centripetal acceleration. That is the acceleration provided by your tires on Nardo Ring or any other circular track. Here's a visual summary of it. Go ahead and draw in a circle. Your acceleration is toward the center of the circle. That's what centripetal means. Here's your position vector, kind of underneath all of it. Your velocity is straight up. This is the 3 o'clock position. Right? The acceleration, v squared over r, and you have to control v with the brakes and the gas. and the design of the track sets you. And once you do that, you've got to set the gas and the speed and the brakes so that you don't go off the track. You can't run it on ball tires. Your tires have got to have a certain amount of grip. Now, here's our last slide, and we'll dismiss early after this slide. We've still got a minute. All right, so here's the centripetal acceleration, and here's the centripetal force. All right, now what we're going to do, and you're dismissed now, we're going to apply this to universal gravitation on Tuesday, 45 seconds early. You're dismissed.